For 4 years, a solitary machine sat on the dusty plains of Elysium Planitia, listening. Not to the howling Martian winds, not to the whisper of ancient riverbeds, but to something far deeper, something that would change everything we thought we knew about the Red Planet. In November 2018, NASA's InSight lander deployed the most sensitive seismometer ever sent to another world, and what it heard defied every prediction. Mysterious vibrations, rumbles from the abyss, sounds that shouldn't exist on a planet scientists once called geologically dead. But here's what makes this discovery truly revolutionary. These weren't just random noises, they were messages, encoded transmissions from the Martian interior, revealing a world beneath the surface that scientists didn't expect to find. A world that's rewriting planetary science textbooks right now. Before InSight touched down on Mars, our understanding of the planet's interior was based almost entirely on educated guesses, mathematical models, and assumptions borrowed from Earth's geology. Scientists knew Mars had differentiated into layers billions of years ago, separating into a metallic core, silicate mantle, and rocky crust like Earth did. But the details remained frustratingly unclear. How thick was the crust? Was the core fully liquid or partially solid? What was the mantle's composition? These questions had lingered unanswered for decades because we had no direct way to peer inside Mars. On Earth, seismology revolutionized our understanding of planetary interiors starting in the early 20th century. When earthquakes shake our planet, they generate seismic waves that travel through different materials at different speeds. By measuring how these waves bend, reflect, and slow down as they pass through Earth's layers, seismologists created the first accurate maps of our planet's core, mantle, and crust. This technique transformed geology from surface observation to deep interior science. Mars presented a unique challenge. Unlike Earth with its global network of thousands of seismometers, InSight was a single station, listening from one location. Making matters more complex, Mars is seismically quieter than Earth. Our planet's tectonic plates constantly grind against each other, generating thousands of detectable earthquakes annually. Mars has no plate tectonics. Any seismic activity would come from thermal stresses as the planet slowly cools, ancient geological structures settling, or meteorite impacts. Before InSight, scientists debated whether Mars was seismically active enough to generate useful data at all. Some predicted the mission might detect only a handful of events. Others worried the planet might be essentially silent. The seismic experiment for interior structure, known as SEIS, wasn't an ordinary seismometer. Developed by a consortium of European institutions led by France's CNES and IPGP, this extraordinary instrument could detect ground movements smaller than the width of a hydrogen atom. Think about that precision for a moment. If you placed the SEIS on the ground and a Marsquake occurred on the opposite side of the planet, it could measure vibrations so subtle they'd move the ground less than the diameter of a single atom. This sensitivity was absolutely necessary because Mars's seismic activity was predicted to be incredibly weak compared to Earth's. The instruments sat protected inside a titanium sphere to shield it from temperature fluctuations that could create false readings, and it was covered by the wind and thermal shield, a protective dome that isolated it from wind interference and the massive temperature swings of the Martian day-night cycle. Every design element served one purpose: to listen to the planet's heartbeat with unprecedented clarity. When InSight began its listening campaign in early 2019, mission scientists held their breath. The first few weeks brought mostly wind noise and instrument settling. Then, on April 6, 2019, SEIS detected its first confirmed Marsquake. It was small, barely magnitude 2.0, but it was unmistakable. Mars was alive, not biologically, but geologically. The planet was speaking, and humanity was finally listening. Over the next 3.5 years, InSight would detect over 1,300 Marsquakes, far exceeding even optimistic predictions. These events ranged from tiny tremors barely distinguishable from background noise to significant quakes exceeding magnitude 4.0 that sent seismic waves reverberating through the entire planet. Each one carried information. Each vibration told a story about what existed beneath the rusty surface.
The sounds InSight detected weren't sounds in the traditional sense. Marsquakes don't create audible noise that human ears could hear standing on the surface. Instead, they generate seismic waves, vibrations that travel through solid rock and can be measured by sensitive instruments. Scientists record these waves as data, waveforms showing how the ground moved over time. But here's where it gets fascinating. When researchers speed up these recordings and convert them to audible frequencies, they do create sounds, eerie, haunting tones that seem almost alive. Some sound like distant thunder rolling through an empty cathedral. Others resemble the creaking of ancient ice or the groan of massive structures settling under immense weight. These sonified versions aren't scientifically necessary, but they give us an emotional connection to what's happening 400 million kilometers away. They remind us that Mars is not a static, dead world, but a dynamic planet still evolving. The real scientific value, however, lies in analyzing the raw seismic data. When a Marsquake occurs, it generates two primary types of body waves that travel through the planet's interior. P waves, or primary waves, which are compression waves that travel fastest and arrive first at the seismometer, and S waves, or secondary waves, which are shear waves that travel slower and arrive second. The crucial difference: P waves can travel through both solid and liquid materials, while S waves can only propagate through solids. This fundamental property became the key to unlocking Mars's secrets. By measuring when these different waves arrived at InSight's seismometer, calculating their travel times, and analyzing how their speeds changed as they passed through different layers, scientists could create the first direct measurements of Mars's interior structure. It was planetary CT scan technology, using earthquakes instead of X-rays. The first major revelation came in July 2021 when 3 separate research teams published groundbreaking papers in the journal Science, presenting the first direct measurements of Mars's crust, mantle, and core. The findings were stunning. Mars's crust turned out to be significantly thicker than most models predicted, ranging between 20 and 70 kilometers deep, depending on whether it consisted of 2 or 3 layers. This thick crust suggested Mars experienced extensive volcanic activity early in its history, building up massive amounts of solidified lava. The mantle extended roughly 1,500 kilometers beneath the crust, composed of silicate rocks enriched with iron, similar to Earth's mantle, but with subtle differences in mineral composition that revealed Mars's unique formation history. But the core measurement shocked everyone. Using data from Marsquakes on the opposite side of the planet from InSight, scientists detected P waves that had traveled completely through the core and emerged on the other side. The travel time indicated a core that was unexpectedly large, approximately 1,800 kilometers in radius, nearly half the planet's total radius. This was significantly larger than pre-mission estimates. More surprisingly, the core appeared to be entirely liquid. No S waves passed through it, suggesting no solid inner core like Earth possesses. This massive liquid core had profound implications. For a core that large to remain molten over 4.5 billion years, it would need a substantial percentage of light elements like sulfur, oxygen, carbon, and hydrogen mixed with iron and nickel. These light elements lower the melting point, allowing the core to stay liquid despite Mars cooling over billions of years. Then, in September 2023, everything changed again. A team led by seismologist Henri Samuel from the Institut de Physique du Globe de Paris published research that fundamentally challenged the 2021 findings. They had discovered something extraordinary hiding in InSight's data:
evidence of core transiting seismic waves that previous analyses had missed. These waves, generated by two large Marsquakes on the opposite side of the planet from InSight, had traveled all the way through the core, bounced off the core mantle boundary on the far side, and returned through the core again before reaching the seismometer. This complicated wave path meant researchers could analyze not just when the waves arrived, but how they had been altered by passing through the core twice. The results were shocking. The waves arrived 50 to 200 seconds later than they should have if passing through the previously calculated fully molten core. This delay could only mean one thing: the core wasn't as large or as simple as initially thought. Further analysis revealed the truth. Mars has a two-part core structure, just like Earth. The outer core is indeed liquid, composed of molten iron-nickel alloy mixed with lighter elements. But inside that liquid outer core sits a solid inner core, approximately 600 kilometers in radius. This inner core is denser, composed primarily of iron and nickel, with fewer light elements. And crucially, it's solid despite the extreme temperatures, because the immense pressure at Mars's center forces the atoms into a crystalline structure. The discovery was published in Nature in 2025 and represented one of the most significant findings in planetary science in years. It meant Mars was far more similar to Earth than anyone suspected.
This revised understanding completely transforms our model of Mars's interior structure. The liquid outer core is now estimated to be around 1,100 kilometers in radius, smaller than originally calculated, which means the mantle is correspondingly deeper and more extensive. This has cascading implications. A smaller, denser core means different heat flow patterns through the planet. It affects how Mars's magnetic field might have functioned billions of years ago, when the planet still had one. It influences our understanding of how Mars formed and differentiated in the early solar system. The solid inner core finding was particularly unexpected because of Mars's size. Earth has an inner core because our planet is large enough to maintain the extreme pressures necessary to solidify iron even at temperatures exceeding 5,000 degrees Celsius. Mars is roughly half Earth's diameter and only about 11% of its mass. The pressure at its center is much lower. For Mars to have a solid inner core means the composition and thermal conditions are precisely balanced in ways scientists didn't predict. It suggests Mars's core cooled more efficiently than models indicated, or its composition differs from assumptions in subtle but critical ways. But the revelations didn't stop there. In August 2025, another research team published findings in Science that used InSight's Marsquake data to probe even deeper mysteries of the Martian interior. They discovered that Mars's mantle isn't uniform. Instead, it preserves ancient heterogeneities, chaotic variations in density and composition scattered throughout its depth. These aren't random fluctuations, they're the preserved remnants of colossal asteroid impacts that struck Mars billions of years ago during the late heavy bombardment, a period roughly 4 billion years ago when the inner solar system was pummeled by massive space rocks. When these giant impactors struck Mars, they didn't just create craters on the surface. They were so energetic that they injected debris deep into the planet's interior, some fragments penetrating hundreds of kilometers into the mantle. Over billions of years, these foreign materials have been slowly mixing with the surrounding mantle through convection processes, but they haven't fully homogenized. They remain detectable as density anomalies that affect how seismic waves travel through different regions of the mantle. This discovery was extraordinary because it revealed Mars's mantle as a geological archive, preserving evidence of events from the planet's violent youth that have been completely erased from the surface by weathering and geological processes. Scientists also discovered something unexpected about Mars's seismic activity patterns. Marsquakes aren't randomly distributed across the planet.
InSight detected clustering of seismic events in a region called Cerberus Fossae, a system of relatively young fissures about 1,600 kilometers from the lander. This area showed repeated seismic activity, suggesting ongoing geological processes. Some researchers proposed these quakes might be related to a mantle plume, a column of hotter rock rising from deep within the Martian mantle, similar to the plume that creates Hawaii's volcanic islands on Earth. If confirmed, this would be evidence of active mantle dynamics on Mars, processes scientists thought might have ceased billions of years ago. The implications are profound. Active mantle convection means heat is still flowing from the Martian interior. It means the planet's geological engine, though much weaker than Earth's, hasn't completely shut down. It raises possibilities that Mars might still have localized volcanic activity in certain regions, or that it could experience volcanic eruptions in the future. These aren't just academic curiosities. Understanding Mars's internal heat flow is critical for assessing the planet's potential to harbor subsurface liquid water and, by extension, the possibility of microbial life existing in underground aquifers heated by geothermal energy. The revelation about Mars's internal structure also helps solve one of the red planet's greatest mysteries. Why did its global magnetic field disappear? Earth maintains a powerful magnetic field generated by convection currents in its liquid outer core. This magnetic dynamo is driven by heat flowing from the solid inner core into the liquid outer layer, creating circulation patterns that generate electrical currents, which in turn produce the magnetic field. Mars once had a similarly powerful global magnetic field, evidenced by magnetized rocks in ancient terrain that preserve the direction and strength of that ancient field. But approximately 4 billion years ago, Mars's magnetic field shut down. The planet lost its protective shield against solar radiation and charged particles from the solar wind. Over billions of years, this exposure allowed the solar wind to strip away much of Mars's atmosphere, transforming it from a potentially warm, wet world into the cold, dry desert we see today. The new understanding of Mars's core structure offers clues to why this happened. If Mars's core cooled more rapidly than Earth's, the convection currents that powered its magnetic dynamo would have weakened and eventually ceased. The smaller core with higher concentration of light elements suggested by the revised models means different thermal evolution patterns than previously assumed. It's possible that Mars's dynamo shut down not because the core solidified completely, but because the temperature gradient between the core and mantle decreased to a point where convection could no longer be sustained. The presence of a solid inner core now suggests this cooling process reached a critical threshold billions of years ago, fundamentally altering the planet's destiny. Have you ever wondered what it's like to listen to another planet's heartbeat? If this journey into Mars's hidden interior fascinates you, hit that like button. Your engagement helps us bring more deep dive space science content like this to curious minds around the world. And if you haven't subscribed yet, join our community of space enthusiasts exploring the cosmos one discovery at a time. Because what we're about to reveal next makes this discovery even more extraordinary. The data InSight collected before its retirement in December 2022 continues to yield new discoveries as scientists develop more sophisticated analysis techniques. Recent studies published in 2025 have revealed additional layers of complexity. Researchers discovered that the Martian crust isn't uniform in thickness across the planet. Regions beneath ancient impact basins like Hellas Planitia show significantly thinner crust, while the massive Tharsis volcanic region sits atop exceptionally thick crust, possibly up to 90 kilometers deep. This variability tells the story of Mars's geological evolution. The thin crust under impact basins reveals where colossal asteroids struck with such force they excavated deep into the mantle billions of years ago. The thick crust under Tharsis shows where extensive volcanic activity accumulated layer upon layer of lava flows over hundreds of millions of years. Each variation in crustal thickness affects local seismic wave propagation, and InSight's data captured these subtle differences. Scientists are also analyzing seismic wave velocities to determine the exact mineral composition of different mantle layers. The speed at which seismic waves travel through rock depends on its density, temperature, and mineral structure. By comparing observed wave speeds with laboratory measurements of different minerals under Martian pressure and temperature conditions, researchers can identify what rocks actually exist at different depths. Early results suggest the upper mantle contains significant amounts of olivine and pyroxene, minerals common in basaltic rocks, consistent with Mars's volcanic history. Deeper mantle regions show evidence of higher pressure mineral phases that form only under specific conditions, providing constraints on temperature profiles throughout the interior. Perhaps the most unexpected finding from recent analyses involves Mars's seismic wave attenuation, a measurement of how much energy seismic waves lose as they travel through planetary materials. High attenuation suggests the presence of partially molten rock or fluids, while low attenuation indicates cold, solid material. InSight data revealed that certain regions of Mars's mantle show higher attenuation than expected, particularly in the mid-mantle zone, between 400 and 800 kilometers depth. This could indicate the presence of small amounts of partial melt scattered through the mantle, pockets of rock heated just enough to begin melting. If confirmed, this would be direct evidence that Mars's interior remains hot enough in certain regions to maintain partially molten conditions billions of years after formation. This has enormous implications for understanding Martian volcanism, past and present. It might explain why some Martian volcanoes, like those in the Tharsis region, appear to have been active relatively recently in geological terms, possibly within the last few million years. It suggests that localized volcanic eruptions could potentially occur in Mars's future, though probably on timescales of thousands to millions of years rather than human timescales.
Another crucial discovery involves the core mantle boundary, the interface where the solid silicate mantle meets the liquid metallic core approximately 1,500 kilometers beneath the surface. Seismic waves reflect strongly off this boundary because of the dramatic change in material properties. By analyzing these reflected waves, scientists discovered the boundary isn't smooth and uniform. Instead, it shows irregular features, variations in depth and sharpness that suggest complex chemical interactions between the core and mantle. On Earth, the core mantle boundary is one of the most dynamic regions of the planet's interior, where ultra-hot core material exchanges heat with the mantle above, and chemical reactions occur between metallic and silicate materials. The discovery of similar complexity at Mars's core mantle boundary suggests this region played a critical role in the planet's thermal and magnetic evolution. Some researchers theorize that irregularities at this boundary might have affected how efficiently heat escaped from the core, potentially contributing to the shutdown of Mars's magnetic dynamo by creating regions where heat flow was disrupted. This is still speculative, but it's the kind of hypothesis that can only be tested with direct seismic measurements, exactly what InSight provided. The detection of Mars's solid inner core also opens new questions about the planet's long-term evolution. On Earth, the inner core is growing slowly over time as the planet cools and more iron crystallizes out of the liquid outer core. This process releases latent heat and light elements, driving convection currents in the outer core that power Earth's magnetic field. Mars's solid inner core might have formed through a similar process, but the key question is, when did it form? If the inner core crystallized early in Mars's history, while the magnetic field was still active, it might have actually helped sustain the dynamo for a time. But if it formed after the dynamo shut down, it played no role in magnetic field generation.
or P wave.
Determining the timing
The
of inner
compression
core
moves along
formation
the spring.
requires understanding the planet's thermal history, which scientists are now reconstructing using the seismic data combined with models of radioactive decay heating, impact heating from ancient collisions, and heat loss through the surface over billions of years. Current estimates suggest Mars's core has cooled by several hundred degrees Celsius since formation, enough to allow significant crystallization of the inner core. The exact composition of this inner core remains uncertain, but it's likely dominated by iron and nickel, with trace amounts of other elements that have specific melting behaviors under Martian core conditions. InSight's seismometer also detected sounds from a completely different source: meteorite impacts. During its mission, SEIS recorded over a dozen impacts where space rocks struck Mars with enough force to create new craters and generate seismic waves detectable across the planet. These impact events provided a different kind of data. Unlike Marsquakes that originate from unknown depths and locations, impacts have known surface locations that can be identified from orbital imagery after the fact. This gives ground truth calibration points. By analyzing how seismic waves from these impacts traveled through the planet to reach InSight, researchers could verify and refine their models of crustal thickness and seismic wave velocities. One study, published in 2025, used impact data to demonstrate that meteoroids strike Mars more frequently than previous models predicted, with implications for understanding surface weathering processes and hazards for future human exploration. But these impacts also served another purpose. Each one was a controlled seismic source, a known location and time that generated waves scientists could trace through the Martian interior with confidence. This helped validate the more complex Marsquake analyses and reduced uncertainty in interior structure models. The implications of InSight's discoveries extend far beyond academic geology. Understanding Mars's internal structure is essential for planning human exploration missions. The thickness of the crust affects where we might drill for subsurface resources. The temperature profile of the interior influences where liquid water might exist in underground aquifers. The composition of the mantle matters for understanding what minerals and metals might be accessible for in situ resource utilization. Even the planet's seismic activity level is practically important because future Mars bases will need to be engineered to withstand Marsquakes, just as buildings on Earth must meet seismic codes. The InSight data provides the foundation for this engineering knowledge. Scientists now know that Mars experiences seismic events up to magnitude 4.7, the largest detected during the mission. While this is relatively moderate compared to Earth's strongest earthquakes, structures on Mars would need to account for these shaking events, especially considering the lower Martian gravity might affect how buildings respond to seismic waves differently than on Earth.
The discovery of Mars's complex internal structure also informs our understanding of planetary formation throughout the solar system. Mars represents an intermediate-sized rocky planet, smaller than Earth and Venus, but larger than Mercury and the Moon. By comparing Mars's differentiation into core, mantle, and crust with what we know about these other bodies, scientists can test theories about how planetary size affects internal evolution. The presence of a solid inner core on Mars, despite its smaller size, was unexpected and suggests that composition might matter as much as size in determining whether planets develop this feature. This has implications for exoplanet science as well. As we discover thousands of rocky exoplanets orbiting other stars, many similar in size to Mars, understanding how such planets structure internally helps us predict their geological activity, magnetic field generation, and ultimately their potential to maintain atmospheres and surface conditions suitable for life. Mars serves as a natural laboratory, a nearby example we can study in detail to understand the broader principles governing rocky planet evolution throughout the universe. Looking ahead, The scientific community is far from finished with InSight's data. The mission collected approximately 900 gigabytes of seismic data over its operational lifetime, and researchers are still developing new analytical techniques to extract additional information. Machine learning algorithms are being trained to detect smaller Marsquakes that were previously buried in noise, potentially expanding the catalog of events from 1,300 to several thousand. More events mean better statistical analysis and higher resolution mapping of the interior. Scientists are also applying advanced waveform modeling techniques, comparing observed seismic signals with sophisticated computer simulations of wave propagation through different hypothetical Martian interior structures. By finding the models that best match the observed data, they can constrain properties like temperature gradients, mineral phase transitions, and the presence of any seismic discontinuities within the mantle. Some researchers are investigating whether InSight's data contains evidence of seismic anisotropy, directional dependence in seismic wave speeds that would indicate aligned mineral structures or flow patterns within the mantle, revealing ancient convection directions or stress patterns frozen into the rock. The future of Martian seismology looks incredibly promising, despite InSight's retirement. Scientists are already planning the next generation of Mars seismic missions. Multiple proposals exist for deploying a network of seismometers across Mars's surface, potentially 4 to 6 stations distributed globally. Such a network would revolutionize our understanding by allowing triangulation of Marsquake locations with high precision, detailed mapping of lateral variations in mantle composition, detection of smaller seismic events through networked sensing, and comprehensive coverage of the planet's seismic activity patterns. Some proposals envision combining seismometers with magnetometers to study potential correlations between seismic activity and magnetic field variations. Others suggest deploying seismometers in seismically active regions like Cerberus Fossae to capture high-quality recordings of the most energetic Marsquakes. There are even concepts for drilling seismometers into the Martian subsurface to reduce noise from surface temperature variations and wind, potentially achieving even greater sensitivity than SEIS. These future missions would build on InSight's legacy, using its discoveries as a foundation for even more detailed investigations of the red planet's interior. The sounds from inside Mars revealed something scientists didn't expect: a planet that's far more complex and active and Earth-like than anyone imagined. A planet with a layered core structure that mirrors our own. A planet whose mantle preserves a 4 billion-year-old record of catastrophic impacts. A planet that still trembles with geological activity driven by heat flowing from its depths. This isn't the dead, static world that dominated scientific thinking for decades. This is a dynamic planet, still evolving, still changing, still very much alive in geological terms. If you've made it this far on this deep dive into Mars's hidden world, you're clearly passionate about space science. Subscribe to join thousands of others exploring the universe's greatest mysteries with us. New discoveries are announced regularly, and we break them down with the scientific rigor they deserve. Hit that subscribe button and bell icon so you never miss the next revelation about our cosmic neighborhood. Because as we continue to listen to the sounds from inside Mars, who knows what other secrets the red planet will whisper to us. The story of InSight's seismometer is ultimately a story about human curiosity and ingenuity. For thousands of years, humans looked up at the red planet as a mysterious light in the night sky. For centuries, we wondered if it harbored life. For decades, we sent spacecraft to photograph its surface. But only recently did we finally stop just looking and start listening. We placed an ear to the ground and heard Mars speak for the first time. What it told us was that planets are far more complex than surface observations ever suggested, that to truly understand a world, you must know what lies beneath, that the sounds from the deep, whether seismic waves on Mars or earthquakes on Earth,
carry information that transforms our understanding of planetary science. InSight's mission has ended, but its legacy continues in every paper published using its data, every student inspired by its discoveries, and every future mission designed based on what it taught us. The mysterious sounds from inside Mars weren't mysterious at all. They were science in its purest form, nature revealing its secrets to those patient enough to listen.